Hello friends, today we will look at natural sampling. Recall that sampling is the process of obtaining a discrete time signal from a continuous time signal. We have already seen how is ideal sampling or impulse trend sampling performed, and we have also looked at the sampling theorem as established using ideal sampling process. Let us now look at one of the practical ways of sampling, and that is natural sampling. Natural sampling is achieved through a high-speed switching process. The message signal is applied to the switch, and when the switch closes, we get the message signal, and when the switch opens, we don't get anything. And this way, we get a sampled version of the message signal in which the message appears in the form of pulses with the pulse stop following the message profile. This process is called natural sampling because the pulse stops follows the message shape. Mathematically, it can be thought of as the message signal multiplied by a periodic pulse train with the period Ts and width of the pulse as capital T. The basic pulse is represented here, which is a rectangular pulse of height 1 and width capital T centered at the origin, and therefore this pulse train S of t can be mathematically represented as summation of the basic pulse pt located at integer multiples of ts, so pt minus some integer n times capital Ts for all values of n from minus infinity to plus infinity. We will now show that for natural sampling also the sampling theorem follows, and if the sampling is done at a rate greater than the Nyquist rate, we can perfectly reconstruct the original message signal. For that, we first need to look at the spectrum of the periodic pulse train and then the spectrum of the naturally sampled signal, which we can denote as M subscript S of t. So let us first look at the spectrum of the periodic pulse train. So the pulse train S of t, which is equal to summation over all n p t minus n ts, can be expressed as a Fourier series summation over all k from minus infinity to plus infinity, Fourier series coefficient ck e to the power j 2 pi k fs t, where fs is the sampling frequency given by 1 by ts. The Fourier series coefficients ck can be obtained as 1 by ts integration over the period ts, which we can select from minus ts by 2 to ts by 2, the signal s of t e to the power minus j 2 pi k fs t dt. Now note that in the interval minus ts by 2 to plus ts by 2, which is from, so this is minus ts by 2 and this is plus ts by 2. In this interval, the signal s of t is 1 in the interval from minus capital T by 2 to plus capital by 2, and it is 0 otherwise, and therefore this can be written as 1 by ts integration minus capital T by 2 to plus capital T by 2, and in this interval s of t is just 1, so it is 1 e to the power minus j 2 pi k fs t dt can be simplified as 1 by ts into 1 by minus j 2 pi k fs into e to the power minus j 2 pi k fs t, and the limits minus t by 2 to plus t by 2. This becomes, when we put the limits here, we get the for e to the power minus j 2 pi k f capital T by 2, that 2 and this 2 will cancel. Similarly, when we put the minus t by 2 value for small t, we actually get the form of the sine function using the Euler's identity. Sine theta is e to the power j theta minus e to the power minus j theta by 2j. When we use that identity here, we get sine pi k fs capital T divided by pi k fs ds, or this can be written as sine pi k fs t upon pi k, since fs into ts is equal to 1. By multiplying the numerator and denominator by fs into t, we can express ck in the form of a sinc function. Let us do it. So we get ck equal to fs t sinc k fs t. Now our pulse train s of t, which in the form of a Fourier series we denoted as k ck e to the power j 2 pi k fs t, it has a Fourier transform that's very easy to obtain using the linearity and time shifting properties of Fourier transform as summation over all k ck delta f minus k fs. That is, the Fourier transform of the periodic pulse train is a sequence of impulses with the strength of each impulse given by the Fourier series coefficient ck, which is a sinc function. Now we can obtain the spectrum of the naturally sampled signal MST. So MST is equal to MT multiplied by ST, the periodic pulse train. We know that multiplication in time is convolution in frequency. So the spectrum of the naturally sampled signal can be written as MSF equal to MF convolved with the spectrum of ST, which is SF, and that is this thing. So this is SF. Accordingly, we get M of F convolved with this summation over all k from minus infinity to plus infinity ck delta f minus k fs. Now we can take MF inside summation using the distributive property of convolution, and we get summation over all k MF convolved with ck times delta f minus k fs, which can finally be written as summation over all k ck m f minus kfs, using the property of impulse function that when a function is convolved with a shifted impulse, we get the shifted function. So this is the spectrum of the sampled signal. Let us look at it on the next slide. So given a signal m of t, let us assume that it is a band limited signal with maximum frequency w. So this is m of f. When this m of t is multiplied with the periodic pulse train, as we have just illustrated, we get the naturally sampled signal mst. It is the result of the product of these two. In frequency domain, the spectrum of the periodic pulse train is a sequence of impulses with the strength of each impulse equal to the Fourier series coefficient, which varies as per the sinc function. So the strength varies as per the sinc function. The spectrum of the naturally sampled signal MSF, which is the convolution of MF with SF, is simply the copies of MF replicated at the integer multiples of Fs. So Fs, 2Fs, minus Fs, minus 2Fs, and so on. The difference compared to the ideally sampled signal here is that here the successive copies of the original spectrum MF gets scaled as per the sinc function, and this is what we get here. Clearly, not all the copies are exactly identical. Their shape is same. However, they have been scaled, but that is no cause of worry. Still, as long as the successive copies of the spectrum do not overlap, this is Fs minus W and this is W. So as long as Fs minus W is greater than W, that is Fs is greater than 2W, these two copies do not overlap, we can still use a low pass filter to extract the original spectrum and therefore to recover the original message signal perfectly. So we see that the sampling theorem still holds even in case of naturally sampled signal or natural sampling. That's all for this lecture. Thank you.